This case study is fisheries. Fisheries are the study of ecological processes that affect exploited aquatic organisms. This can be both marine and freshwater environments. Because fisheries are primarily motivated by an attempt to harvest populations, special attention has been given to understanding the regulation of these populations by nature and by humans. So the foundations of fisheries ecology lie in population and community ecology and bring up numerous concepts that we've talked about throughout the class, including overexploitation, population process and stock assessment, and the challenge of managing common resources, the tragedy of the commons. So first we'll start with the idea of what a fishery is. In managing a fishery, we're talking about not only the resource, the fish, but we're also talking about managing the people and the associated habitat. And the problem of regulating the exploitation of aquatic organisms is that we want to ensure a sustained harvest. This lies at the core of fisheries ecology. Most experts agree that the harvest of marine resources has peaked, and increased yields are likely to come only from fine-tuning regulations on fisheries stocks. A stock is a particular species fished in a particular place. So for example, in the bottom graph you can see fisheries stocks, the Peruvian anchovy, the pollock, herring. Each one of those are managed as a stock. If you look at global fisheries, over 75% of the world marine fisheries catch, which is about 80 million tons per year, is sold on international markets, in contrast to other food commodities like rice. At present, only one institution in the United States, which is the Food and Agricultural Association of the United Nations, FAO, maintains global fisheries statistics. These numbers, that a lot of them that I present, are from the FAO or from other papers, because the FAO generally relies on statistics provided by their member countries, even if it is recognized that it's doubtful that these correspond to reality. What they do show in terms of global marine fish yield is that many, in fact most, countries have, most fishery stocks have widely fluctuating catches that have been declining over the past years. But the first problem that we talk about with these numbers is we're managing a resource where we have a lot of uncertainty in the numbers. This is a time series from a Pew report that looks at global fisheries and looks at Chinese catch. We talked about this in the case study looking at whaling. The global reported catch with and without the highly variable Peruvian anchoveta is shown, and they're uncorrected. But basically what they show is that in Chinese policy, these are reported Chinese catches from China's exclusive economic zone, increased exponentially from the 1980s to 1998, when the zero growth policy was introduced. These show that they are reporting mandated catches because socially they felt like they needed to catch more fish and meet those. So here we even have an instance of where population numbers are inflated, causing even more uncertainty. What's driving these numbers? This is again FAO data, looking at the total kilograms of fish per capita, showing that these are increasing over time as a total number. But if you look at the breakdown between wild and farmed, you can see that we've actually been declining in wild catches as a result of fisheries declines. So what does fisheries science tell us about this? The early history of modern fishing was characterized by attempts to ensure an increasing supply of organisms at all costs. In the early remarks to the fisheries exhibition, people commented that fisheries were inexhaustible. We knew that fish moved with ocean currents and felt like this could help us describe where fish occurred. In the last 2 decades, this view has modernized to a more realistic perspective, increasing natural limits to aquatic resources, and understanding of environmental aspects. Environmental aspects like the idea shown in these two graphics that increased primary productivity in terms of phytoplankton leads to increased fish production. All of the black zones shown on the map correspond with very productive fisheries. What do we know now that is applied to fisheries management beyond just we can't eat all the fish in the sea, which we know isn't true? Well, the first idea is, again, this definition of stocks that I talked about in the beginning. A stock is a group of exploitable organisms that is physically or hydrogeographically constrained. So that means it's defined by both a species and a geographic area. This is the typical unit at which management efforts are directed. It's the exploited population, or the stock. An essential aspect of assessing fisheries resources is to identify these stocks and determine how isolated they are from other stocks of the same species. For example, you can have the North Sea plaice or the Pacific hake. There's also 20 major recognized stocks of cod in the North Atlantic, each on the whole isolated from one another and distinct with regard to several biological characteristics that help us determine the potential for harvest. This does mean that fisheries management is very single species focused, lacking some of the ecosystem-based management that we've talked about for other examples. What sort of data do we need for fish stock assessment? We need population size. This is typically estimated from landings or fisheries take as a catch per unit effort. How many fish do we get per man hour? It can also be done with mark recapture methods, which is purely a scientific method, but has a really low recapture rate. We also would like to know something about growth rates of the species, which means we need to know something about all the factors listed here: food availability, habitat quality, physical forces, competition, predation, disease. We need to know something about survival or mortality, both natural and anthropogenic. And we need to know something about recruitment. And it's in this recruitment category that a lot of fisheries stock assessments are based. Maximum Sustainable Yield, or MSY. These are also known as Schaefer models, and this requires you to think back to what we know about population growth. If we look at a logistic model of population growth, shown in the top graph as time versus population biomass, we are all familiar with the idea of density dependence that can be introduced via competition, disease, or cannibalism. And the idea is that if you look at this as a change through time, shown in the bottom graph, you want to find the point where the stock is replacing itself as fast as it is being taken. This would be assumed to be right before carrying capacity. And it is known as the maximum sustainable yield. And the idea in terms of fisheries is that a fisherman's perspective is if you are allowing fish to die off because they've reached carrying capacity, that is wasted fish. You want to fish out those fish before the fish is lost to old age or eaten by another individual. So you want to make sure that you're fishing at the maximum just below carrying capacity level. Is this any good? Well, in theory, I just explained it to you in a minute. It's very easy to understand. It jives with population ecology. And it emphasizes that you can't just fish to an ever-increasing level. There is some optimal fishing level. It's also a very clear and easily defined objective. However, there are distinct disadvantages. It assumes that the starting population is not already below the environmental carrying capacity, that there aren't other factors limiting its ability to reach that point, like an Lee effect. It also assumes that instantaneous equilibrium can be achieved, i.e., there's no lag time in population growth. It has no assumptions or no information about age or stage structure. It doesn't incorporate stochastic or random components. It eliminates some very important interspecific factors like competition and predation. It doesn't account for human drivers of socioeconomics, and sometimes it doesn't actually even focus on sustainability. There are more complicated alternatives to it. This considers age-specific growth and mortality rates, and it has to use specific stock assessments and estimates of recruits. It has a very it has a more complicated equation and modeling. It's known as the Beverton-Holt model. How good is it? This is just an example of what a graph looks like as opposed to the Schaefer MSY model that I showed you. It is much more realistic biologically. It considers stocks that are fished or unfished, and it can make different rules for different ages. However, as you can even see from the graph, it's much more complicated. It requires more detailed data collection, and it makes an assumption about steady state. We also know that even just this idea of managing a single species or a stock is complicated because of the natural complexity of multi-species fisheries. In this example, you have the ability or the disadvantage of having to monitor multiple exploited species at the same time. So that's the science, in brief, behind how fisheries management is conducted. There's also a legal and management side that have to do with laws. Focused on the United States, the federal legal authorities that are relevant to fisheries laws draw from at least 7 narrowly focused laws. These are not coordinated with each other. They have at least 7 federal agencies, which tends to lead to a sort of incoherent and chaotic approach. The number one fisheries law that people usually focus on is the Magnuson-Stevens Fishery Conservation and Management Act. It governs the fishery management system. It does include some aspects of human and social components, the socioeconomics, but it has minimal conservation. It deals a little bit with minimizing bycatch, and it deals a little bit with the fishing effects on habitat, but not enough. So at the state level, there's the California Marine Life Management Act, which attempts to apply a more ecosystem-based approach to fisheries law. And what are the impacts of fisheries? Similar to other exploited populations, there's direct effects of reducing the abundance of fish. And I'll go through examples of these later. It reduces the age of maturity by removing or selecting against the largest individuals, thus changing the genetic structure of the population and the recruitment. It can also change range and reproductive potential, and ultimately lead to extinction. It has ecosystem effects of fishing down the food web, causing trophic cascades, and removing prey for other complicated food webs. Indirectly, the impacts of bycatch and habitat loss are also significant. If we look at some of these individually, this is looking at sort of the worst case scenarios of that decreasing abundances. That an unexploited population, while it has variability, can deal with environmental variation and continues, and the exploited populations could crash and lead to extinction. This is a calculation of mean trophic level, which looks at multiple steps within the food web, potentially excluding the microbial portion. And you can see that there's been a significant decline in both marine and freshwater fishing, because fishing is selectively removing large individuals and species, thus reducing that overall trophic level within the system. How are these impacts accomplished? They are done, as we looked at with other exploit examples, through increasing take, few rules, and increasing technology. This is the example of mechanisms behind the demise of the bluefin. And in some ways, people have compared, the bluefin tuna fishing to the Wild West of fishing, in which the fishermen, the traders, and the regulators have for years widely just ignored the rules. At its peak, which was around 1998 and between 1998 and 2007, there was a large black market for tuna. People estimated that 1 out of every 3 bluefin caught were actually entering the black market. This was done partially because of widespread fraud, overfishing, and the rise of technology like spotter planes and fast shipping that enabled the fish to be in market with short periods of time. But it's not just the bluefin tuna. If you look at the catch per unit effort shown in each one of these graphs for different species of tuna across different regions, you can see an overall decline in the number of fish that are caught. Outside of these fishing techniques, there's also very destructive methods that are used by fisheries in order to catch fish. One very common destructive fishing method is the use of dynamite, often referred to as blast fishing. This involves the use of a bomb set to explode underwater in a coral reef. When it detonates, it kills or stuns the majority of fish within its radius, and those fish float to the surface where they can be easily caught. Unfortunately, this highly illegal practice of blast fishing is commonly used in over 30 countries and has caused major damage and loss of coral reef ecosystems, including 50% of the reefs in Southeast Asia. This is particularly damaging because not only does it reduce the fish levels, it shatters the reef structure. So you're losing the ecosystem itself. It takes an estimated 100 years of recovery to rebuild itself, for a reef to rebuild itself after destructive blast fishing. In the similar category, a different but commonly used method of fishing is cyanide fishing. Unlike blast fishing, cyanide fishing does not destroy the physical structure of coral reefs, but causes irreversible damage in other ways. It poisons fish until they become stunned, making them easier to catch. It was developed in the 60s. It involves crushing a tablet, mixing it with salt water, and storing it in bottles where it's illicitly put into the reef's habitat. It's commonly used for capturing fish for the aquarium industry, but it affects a lot more than the fish caught. It's poisonous to the coral polyps and kills off their source of food. It also is a threat to the surrounding marine life, killing fish eggs as well as adult fish. Another fishing method is fishing out spawning aggregations. So fish spawning aggregations occur for a number of purposes: spawning, feeding, or protection from predation. It's basically a group of fish gathered for some purpose with individual densities that are higher than those normally found in non-reproductive periods. Many different fish species spawn in these spawning aggregations, leading to evidence that there's evolutionary advantages to aggregating. What it does do is provide, if you know the timing and the location of these aggregations, they can easily be fished all at the same time. What this does is remove fish before they have a chance to reproduce and remove many of the large individuals. So it is a potentially very productive fishing practice, but very destructive for the overall population. Studies have looked at the implications of these, and this was a study from the Gulf of California that investigated the associations between the timing of spawning aggregations and monthly trends in commercial landings and vessel revenues, and compared this through time. The species that were known to form seasonal spawning aggregations comprised 8 of the most important commercial reef fisheries in the Southwest Gulf. And what you saw was that peaks in monthly landings and revenues for 5 of the 8 aggregating species coincided with the timing of their spawning aggregations. So they were suspecting that despite outlawing this, fishing of the spawning aggregations were still going on. And these are many of the species that we see in ceviche and other fish that we eat. So they are entering the market. Another challenge with fisheries with fisheries is bycatch, the incidental catching, discarding, or damaging of living marine resources that are not targeted within the fisheries. Shrimp trawls are one of the worst examples of bycatch. They can have as much 85% of their total catch is actually bycatch. There have been efforts to deal with this. This is an example in a shrimp trawl of a release hole for non-shrimp bycatch. Shrimp are much smaller than the large fish. They can pass through a grate like this, whereas other species go out and over. There's also species with low reproductive rates that suffer the most. So these are examples of cetaceans, sharks, turtles, and albatross that are caught as bycatch. Another portion of the fishery that's not very well managed by fishing regulations is ghost fishing. Fishing gear gets lost or stuck on the bottom very often and is often just cut or discarded, and it can continue to fish for years and years. Monofilament itself is hard to see and doesn't break down. And the last aspect that isn't necessarily dealt well with in fisheries manages is this habitat disturbance and alteration. By dragging a trawl, which we've talked about in class, you have heavy boards and chains that raise the fish off the bottom and into the net, but at the same time they're very destructive to a lot of slow-growing marine organisms like deep-sea corals, gorgonians or ivory tree corals, and people have done before and after trawl pictures showing these sort of reef structure before a trawl on the left and after a trawl on the right. There's also a significant amount of fisheries that occur around features like seamounts, which are mountain peaks on the ocean floor. Fish like orange roughy aggregate there. They're very slow growing and they again can be fished out by fishing on seamounts and features. This is an example of, all the seamounts that are in the ocean that are well mapped and the fisheries that can, occur around these if they're targeted. And some of the species that people have found are inadvertently affected by trawling at these depths. Another aspect of fishing that's not necessarily well dealt with is the idea that when people are fishing using bait from shore, they may also inadvertently be introducing non-native species to the ecosystems. These are just some examples of non-native species that have been introduced through the fishing trade. So what I've tried to do is highlight the examples of how fisheries work and where they don't work very well at the end. The strategies that we need to put in place are first managing the fish, dealing with the idea of increasing the carrying capacity of the system. We can do this by increasing primary productivity, i.e. food sources, or top-down, removing the threats to the predators, including non-natives and some of the destructive fishing methods I talked about. We also need to manage the habitat, protecting some examples like I talked about of the spawning habitat or the environmental conditions that support fisheries. And then we also need to manage the people, dealing with all sorts of regulations, catch limits, size limits, gear type restrictions that may help influence what people take. So some of those examples are these depths and gear strategies where you can use depth offshore and depth of the lines to target different fish species. If you keep the hooks out of the surface water, you can avoid some of the bycatch that you would get if you left them at the surface. You can also use devices that are similar to what I showed you for the shrimp trawl and our turtle exclusion devices. There's research going on in Baja looking at how visual clues play important roles in sea turtle foraging and likely influence their interactions with fishing gear. So altering these cues may be a useful strategy to reduce the incidental catch of sea turtles. Looking at shark shapes in daytime experiments placed on gill nets. Looking at the illumination of nets by LED lights or chemical glow sticks. All of these can help reduce the bycatch of green sea turtle. There's also solutions to these that are just making us more informed consumers. This is from the Blue Ocean Institute. It also exists from the Monterey Bay Aquarium. But as informed consumers, we can look more at what seafood we're purchasing and where it comes from. So for the case study that we're going to be doing in class, I'm going to introduce a real patent that would talk about iron fertilization. I'll give you the details in class, but have you evaluate that as a bottom-up strategy for managing the fish from a science perspective and from a habitat and human perspective.